Today we are explaining the paper learned from your own latent tests and not from tokens, a sample complexity theory.
What is the central question?
Modern generative models learn by predicting tokens, such as a missing word or image patch, and they need enormous datasets. This paper asks whether predicting a model's own hidden representations can discover hierarchical structure with far fewer training samples.
Why would predicting tokens be inefficient?
A token sits at the bottom of a compositional hierarchy. To learn a high-level concept from that token, a token-level objective must detect a weak statistical correlation across many levels. In the paper's model, that signal shrinks with tree distance, so the required number of samples grows exponentially with hierarchy depth.
What kind of hierarchy? What's the authors measure that effect?
They use the random hierarchy model, a probabilistic grammar that generates a visible sequence from a hidden tree. The tree has depth though. Each parent expands into one of m allowed child tuples, and each level has v possible hidden symbols. The leaves are the only tokens shown to the learner.
Where do latent representations enter this grammar?
Different child tuples can come from the same hidden parent. The paper calls those tuples synonyms because higher levels use them interchangeably. Recovering the hidden hierarchy means recognizing which tuples are synonyms, assigning them the same latent label, and then repeating that operation one level higher.
How does the paper recover those synonym classes without using the hidden labels?
The first method is iterative latent clustering. For every tuple, a predictor estimates the distribution of nearby cousin tokens. Tuples with the same hidden parent have the same expected cousin context, so a cluster groups their prediction vectors. The resulting cluster identifiers become the tokens for the next iteration.
Why does repeating the operation change the sample complexity?
After one level is clustered, the next level no longer has to reach all the way down to tokens. It receives newly discovered latent labels as its input and solves another local prediction problem of the same difficulty. The same training set is reused at every level, so depth adds iterations but does not multiply the number of distinct samples needed.
What does the theoretical guarantee say?
Under a balanced and separated random grammar, and assuming the clustering algorithm is stable to small estimation errors, the method recovers every hidden level below the root with high probability. The labels may be permuted, but the recovered grouping is correct. The sample bound makes the key contrast precise.
Which parts of that bound matter most?
P is the number of training strings. The dominant term is proportional to v times m cubed, while depth L appears only inside a logarithm. Delta controls the allowed failure probability, and 1 minus f measures how strongly different parent contexts remain separated. This is the paper's depth-independent sample complexity claim.
Is iterative latent clustering only a hand-designed algorithm?
The authors also build a differentiable stacked latent clustering network. Each module contains a predictor and a clusterer. The predictor learns cousin token distributions, and the clusterer maps similar prediction vectors to the same soft code. Stacking one module per hidden level mirrors the iterative algorithm and can be trained end-to-end with gradient descent.
What stops the clusterer from assigning everything to one code?
Its clustering objective has opposing pressures. Similar prediction vectors are pulled into the same code. Dissimilar vectors are penalized if their assignments overlap, and the sparsity term encourages decisive assignments. Together, those terms make the learned codes behave like discrete latent symbols instead of collapsing to one cluster.
Where does data to VEC fit into the argument?
Data to VEC masks visible positions in a student network and asks the student to predict pooled hidden representations from a teacher network. The paper argues that once the teacher represents one latent level, those targets contain information about that level. Gradient descent can then extract the next detectable correlation, creating a sequence of implicit latent learning phases.
So does data to VEC need an explicitly stacked hierarchy?
Not in this model. A single data to VC training objective can discover the levels one after another because its own representations become progressively richer. Targets. That leads to the same v times m cubed sample scaling. The paper therefore argues that explicitly stacking a separate latent prediction objective at every scale may be redundant. Now we can test the main scaling claim. The left plot measures direct iterative clustering.
What evidence in the curve supports the theory?
Before rescaling, larger m values require many more samples. After dividing the horizontal axis by v times m cubed, the transition curves line up. The insets also show that the sample count needed to cross 50% accuracy follows m cubed, rather than the exponentially larger token prediction scaling. The authors then test data to VEC. They freeze the pre-trained encoder and train a probe to predict the hidden root label from its final representation.
Does data to VEC match the explicit clustering methods?
Yes, the Y curve shift as m changes, but they collapse when the sample axis is divided by v times m cubed. The inset's threshold points also track m cubed and stay far below the token level prediction rand. That is direct evidence for the paper's claim that data to VEC performs implicit hierarchical latent prediction. Root classification alone could hide the mechanism. So the paper also measures whether data to VEC's internal representations place synonyms closer together.
What does the synonym score reveal across the levels?
The score becomes positive first for the lowest hidden level, then for the next level, and finally for the deepest measured level. Each transition occurs around the same rescaled sample scale. This ordering supports the proposed mechanism. Data to VEC discovers lower level synonym classes before higher level ones, but reuses the same dataset for every phase. The stat network shows the same sequential behavior during training.
How does this block connect prediction to clustering?
Each solid accuracy curve rises in order from the bottom layer upward. When one layer begins clustering correctly, the dashed prediction loss for the following layer falls, giving that next layer a cleaner target. The network is trained end-to-end, yet learning organizes itself into the same bottom-up phases as the iterative algorithm. A final comparison deliberately rescales the same clustering results using the token-level prediction law.
What goes wrong under the token level scaling?
The curves no longer align. Their transitions spread across the horizontal axis instead of collapsing onto one threshold. That failed collapse matters because it distinguishes the paper's latent prediction law from the exponentially depth-dependent law already known for token-level self-supervision.
What are the main limits of the result?
The theorem is for stylized random grammar with balanced production frequencies, separated context vectors, and a stable clustering procedure. The data to VEC theory also assumes that teacher targets carry already learned latent tests and that gradient descent extracts correlations once they rise above sampling noise. Those assumptions explain a mechanism. They do not prove the same scaling for natural language or images.
What is the strongest takeaway?
The paper gives a concrete reason to predict learned representations instead of only raw tokens. By turning recovered structure into the target for the next level, latent prediction avoids repeatedly estimating long-range, weak correlations on the random hierarchy model. That changes the sample requirement from exponential in depth to roughly v times m cubed, with depth entering only through logarithmic factors.
So the important result is not just that latent prediction works, but that each learned level makes the next level statistically easier without demanding a new, exponentially larger dataset.
Exactly. That wraps up this paper explanation.